We are back to another workshop, how to program a HMI using PanelView 800 graphical terminals. These graphical terminals are from Rockwell Automation. There are three series, but in this workshop, we are using the 7-inch graphical terminal. So you should note here, for any standalone machine operations, HMIs are widely used in industrial automation. Not like in SCADA systems where you have multiple machines and overall visualization of the factory with many industrial machinery and workstations connected through different communication links. More often, we need to work with standalone machines like a small PLC or your VFD drive connected to a specific task at a smaller scale. So in that case, HMIs are widely used. So in Rockwell Automation, they offer PanelView 800 graphical terminals. They have high-speed processors and high-resolution displays, which is ideal for standalone machine development. So we can see here like a small application. This is our PanelView 800 graphical terminal. And so it is connected through Ethernet. And we have this Micro 50 controller. And this is our computer, which has the connected component workbench. You can visualize all the parameters and program this HMI and the PLC through the Ethernet. And this is a VFD drive for Flex series, which supports the Ethernet. So you can connect multiple machines through Ethernet. And this PanelView also support Ethernet communication. So it also has some other communication channels as well, like RS-232, RS-422, and RS-485. Or it can use Ethernet IP. So to program this Micro 20 PLCs and PanelView 800 graphical terminals, there's a one open source software package that is known as the Connected Component Workbench, also known as CCW. So if you already use CCW to program your PLCs, now it is one step ahead just to program the HMIs. In CCW, we have the design station. It's another part of the CCW. So if you use a design station, you can easily program your HMI for given application. So PanelView 800 graphical terminals comes with different sizes, 4-inch, 7-inch, and 10-inch. In our application, we are going to use 7-inch display. So it is a touch screen running with TFT touch and white LCD, and it can run up to 40,000 hours and 65K colors, and run at a 800 megahertz frequency, and it has a memory of 256 megabyte of RAM and 256 megabyte of storage, and supports Connected Component Workbench. So more technical details on PanelView 800 terminal can be found in this technical data sheet. If you refer it, you can find out more details. Coming back to the workshop, here I'm just giving you a hardware overview of this PanelView 800 terminal. Just to note, this is the 7-inch terminal. So if you take a look at this, is how it looks like in the front view. So you have this power status LED when you're powering up the HMI. So this LED will lit. This is your touch screen. And number 3 is the mounting slot, because this is panel mount. So you can mount this on a panel. And number 4 shows you communication channels. It could be RS-422 and RS-485 ports. And also it has a RS-232 port. And it also contains the Ethernet port. You can see here, number 6 is the Ethernet port. In this practical, we are using the Ethernet communication, so we are not using any serial communications. And number 7 is the replaceable real-time clock battery. So, like when the power is off, still to run and save the data, save the time, display the time. It has a real-time backup battery. And this is 8 is the USB port. 9 shows the diagnosed status indicator. And 10 is your SD card. Sometimes you can download your code to this SD card and keep it running. 11 is your input power. So you have to provide power to this terminal. 12 is your USB device port. So 12 is USB device port and 8 is USB host port. So these are the technical details just we have covered. You have to note here, you have to power it with 24 volt DC to this socket. In these terminals, so one is connected to the earth or the chassis that can be connected to your panel for earthing, and plus DC goes to your 24 volt and minus DC goes to your ground. First step in this workshop is to configure your graphical terminals with your language preference. You can select English language and you can set the data. And now you can set up the communication. So you have to go to the terminal settings in the main menu and press the communication. If you press the communication, then you can come to this communication display. Here you have to first disable the DHCP and set the IP address. So you have to provide a static IP. So in the range that you are using in your PLCs, so it should not be a IP address that is already assigned to any PLC device or your computer. It should be a different IP address and with the same subnet mask. Once you configure the graphical terminal with the Ethernet settings, then you can program it. So in this example, IP address is specified in this way, but this might not be the IP address that we are using in our lab. So get the support from the instructors to configure the correct IP address. Now you have to open the connected component workbench and you can create the HMI program. So there's a one way that you can download this your application, HMI application that you have created your panel view device. Either you can use in the connected component workbench through the Ethernet, or else you can save it to your USB flash drive or micro SD card and insert it into the USB slot in the SD card slot in your graphical terminal. Then also you can execute your HMI application. So these are the instructions to follow for this workshop. There's a small application here. There's a variable frequency drive that outputs 0 to 10 volt analog signal, which is proportional to the speed of the motor. So if you have 10 volts output, which means the motor is running at its full speed. And if you have 0 volt, that should be that the motor is off for stop. So the following operation should be performed. There should be a start push button to turn on the motor and stop push button to turn off the motor. And these push buttons are not mounted on the PLC. These push buttons should be on your HMI panel. So which means you have two push buttons in your touch screen. When you press that, the motor should turn on and off. And you have to insert a motor icon to display that the motor down just top of your start and stop push button. So the user knows that by pressing this start and stop button, that only just to control the motor. A pilot lamp should be used to display the motor on and off status in your HMI. And using an analog gauge, the voltage signal 0 to 10 from the VFD should be displayed on HMI. So in the HMI, there are analog gauge, so you can display whatever the analog signal comes there. So the range could be specified from 0 to 10. So that will display the speed or the voltage signal in your HMI. So after that, you have to use a text field to display the numerical value of this voltage just under the analog gauge. So rather than like the analog scale, just provide you some sort of analog scale is something like that. It has an arrow, goes from here to here. This is your 0 voltage and this is your 10 volt. And text field is something that the voltage, let's say like is 5 volt, it will be just displayed under your analog gauge. And so we have some alarm functions, and also we can display if the motor speed reaches more than 90%. Another pilot lamp should be lit on your HMI. In addition, an alarm panel should display motor overspeed on the HMI. And the motor should acknowledge the alarm signal to clear it. These are the instructions that you have to follow. First, identify the requirement of number of inputs and outputs to implement the system, both in your PLC and HMI. What are your inputs for the PLC and what are your outputs of the PLC? And for the HMI also, there are some push buttons and outputs and inputs. Then you have to create a ladder diagram to solve this problem using Micro 820 PLC and using the connected component workbench. And then you have to create a HMI application. Since it will be more easy and convenient to use a 0 to 10 volts signal without using a VFD, we can just emulate by using a potentiometer and using the 10 volt reference voltage available on our panel. So if you use a potentiometer, that can change the voltage from so just from 0 to maximum 10 volt using your potentiometer, right? Rather than using the VFD alone. After that, you can download your ladder diagram to the PLC and also download the HMI application to your graphical terminals through the Ethernet connection. Then you have to observe the performance and get these observations. First, take a photograph of your test setup and screenshots of your ladder diagram before the downloading, and attach a screenshot of your HMI screen 1. Then display the input-output variable assignment of 2 programs. So in the PLC program also, there is a input-output configuration, and the HMI also, there are some input-output variable assignments. You have to display both of them. And there's a tag list. So in the HMI, when we create in the application, there's a tag list. You have to copy that tag list here. Then you can do this following test. For example, now while the run mode is enabled, get screenshots of the program for different test conditions. Show the status of the start stop pilot lamps both in the ladder diagram and the HMI while the PLC is running, and display VFD voltage signal on the HMI, and display the alarm banner when the motor overspeeds. So these observations has to be taken while you testing your HMI application. Take a look at how we can program the PLC and HMI. First, we need to create a project. Then select the Micro 820 PLC and go to the graphical terminals and panel view 800, and T7T is the correct HMI for this project. So now we have just come to the Ethernet settings and configure the correct IP address of the PLC that your HMI is connected. This could be different from PLC to PLC depending on the panel board that you are working on. Once you configure the separate mask and the IP address, then you can create a new ladder diagram. So now we are opening the ladder diagram. So this ladder diagram might contain several networks, so we can add few networks. First step is we have to use start and stop button to turn on and off the motor. You can add parallel contacts. And normally close contact is used to stop the motor or stop push button. And we are using a digital output to indicate the motor. So the second rung is just to for the ADC, whatever the ADC comes to this particular channel should be converted to a voltage. So you should remember, like ADC for any channel, the maximum voltage to the minimum voltage. So ADC value change from 0 to 4095. So we have to add few rungs here. I will explain them later. Now you should define global variables, two variables. First one is start and second one is stop. They should be Boolean and the variable types, and they are just to control from the HMI. So we have to define them global variable, and the V in variable is of the type real, because that is the voltage that we generating from the PLC and send to the HMI. Now we have to correctly assign these inputs. So the start push button coming from the HMI, coming from the global variable, and stop. These two variables are from the HMI. That's why we defined it as a global variable. So we have set the digital output 0 to light indicator at the PLC. That is just to indicate the motor is started. And from the same coil, we can use the it to latch when the start momentum push button is pressed. Now, when the motor is running, we have to do the ADC, because if the motor is stopped, we are just stopped. We don't need to do the ADC. And so that is just to, when this motor is running, the networks 2, 3, and 4 are operating. So any to real is used because, like the analog input 0, 0 is used here. So whatever that voltage is converted to a real value. So it is now converted to ADC. The variable name is ADC and of the type real. And you have to just, like 0 volt indicates 0 and 4095 indicates the 10 volt. So we have to back calculate the voltage comes to the ADC channel based on this algebraical function blocks. The purpose of network 2 is to read the ADC 0 channel and convert that to a voltage V in. So that is the real type data. Like this calculation is whatever the value comes should be multiplied by 10, then divide by 4095, then you will get the correct voltage value based on the voltage appearing at the analog input 0, 0. So we are just copying that variable to V in real type variable that will be sent through the Ethernet to the HMI. So if the voltage is higher than 9 volt, we can use a higher than or equal conditional statement, and we can assign a digital output 0, 1 to indicate the overspeeding event, or you can type any name. For example, here the error is label is used here. Now, one thing is to note that if the motor is stopped, we have to use a V in, the voltage should be 0. We are just copying that voltage here. Otherwise, the last saved voltage will be updated to V in. So that is what we did in the last round. Now we have just successfully compiled our program. Now we have to create the HMI program. Go to this landscape, select the landscape of the HMI. And the protocol should be Ethernet along with the CIP, and the correct IP address should be set to the PLC1. Make sure you save that same IP address set in the PLC should be set in the HMI communication, because HMI is now communicating to that PLC. So we have to add the tag list. So like the start and stop Boolean type tags are local to the HMI, but we have to share them with our controller. So these, like start PV and stop PV, we have to link with the PLC variables, global variables, start and stop. Then only HMI start button is pressed. That will update the PLC program start and stop, normally open and normally close push button. This is our tag list in the HMI. So we have to add a few more tabs. So I'm going to add the V in tag, that is for our ADC voltage, and that is the type is real, and set it to the PLC global variable list. That is the real voltage comes to the ADC channel when you change the VFD speed or your potentiometer. For overspeed indication, we are again using another Boolean type variable that is linked to the global variable error, or that is digital output 0, 1. Again, the correct PLC is set. This is for overspeeding. So our tag list is updated now. Now we are go to the screen number 1 and design our HMI screen. So you can change the background color to whatever the color you want. And we have to add the momentary push buttons to start and stop the motor. Here you can just copy and paste multiple push buttons. You can size and you can change the colors, and then you can add the motor. So this icon, you can just, if you want, you can enlarge your push buttons. Now go and select from the image import, select image for your motor. You have to go to the motor and then select the whatever the motor that you wish to import. So our motor icon is displayed in the HMI. Now we have to label these start and stop push buttons. The background change, normally for the start button, we can set it to green. You know, like if it is 0 and the same green color is there, if it is 1, you have to use the same green color, otherwise the button color will be changed when you every time you're pressing it. Set the caption tag to start and change the label size to whatever the size you want. So for 0 and 1 bits, the same color is used. Similar thing can be done for the stop push button. You can change the colors to red when you press, or when you not pressed, the same color will be there. That's why we're using red color. You can add the caption text to stop and to change the caption font size. Now we have to link this push button to the correct variables. So in that case, we have to click that, go to the right tag and select the start push button. So whenever you press it, this start push button tag will be updated. For the stop also, we have to select the stop push button tag. So when you're pressing it, that right tags will be updated. Now we are importing the analog gauge. You can resize it to the size you want and change the background color. If you want to use the same color of your background, you can change it from here. So you can hide the borders. Now your size can be from 0 to 10. And the angles can also be changed, and the read tag should be V in. So whenever the input voltage comes, it will change. And appearance color can be changed to whatever color you want. Here I'm changing to black. So angles are set to default. So you know, like it's starting from -30 and 135. And now we have to add the text field to display the analog voltage. So go and insert variable. So we can type V in, or the voltage. And here pick the number and select the tag. So this is our V in tag. So number of digits and number of decimal places that you wish to have. So I'm setting 2 decimal places. Set it to OK. And so this voltage is DC volt, so we can type VDC at the end of the voltage. So it will display the voltage and the correct voltage, correct with the correct units. You can resize to whatever size you want. So now we can go to the alarms. You know, for if there's a overspeed alarm event occurs, we can set the alarm indication. There could be a message for that. the user will update it with. You can add a message for the alarm. Here I'm typing mode over speeding. So that is basically your alarm tag. Now we're coming back to the screen. Now we can validate it. Make sure you save your project. Otherwise there will be compilation error. So here there's a error comes. One warning, communication settings, the address is not configured correctly. We can see what is the address of the PLC. So it is defined, but sometimes it is not updated in the software. So what you can do is you can just again retype it, then it will solve the problem. So you can save it and then compile. So the project is going to be validated. If there aren't any errors, we will get 0 errors and 0 warnings. So our application is ready now for downloading.